Hello, guys, and welcome back to Aerominds Training Center. So now we are starting with the chapter 6, part 2 of Winds chapter. We have already completed the part 1. I hope you guys have watched that, and if you have not, the part 2 won't make sense to you. So I want you to watch the first part before watching this. So we'll uh, do a slight revision before moving on to the part 2. So we'll start with what is wind. So in the atmosphere, air is always in motion, horizontal or vertical. Horizontal movement is called wind. Horizontal differences in the air pressure causes the winds. Okay, air tries to move from area of high pressure to low pressure, which causes winds. And the series of stronger winds are called gust, and weaker winds are called lulls. Now remember, wind has two components: speed and direction. Both are important. And first is direction. So direction is measured from where the wind is blowing. Now if the wind is blowing from southerly, so if it is a southerly wind, it is blowing from south to north. If it is easterly, so east to west. Then comes the compass direction. So there are 16-point compass. These are the directions. Then degrees, which are measured in clockwise from true north, and usually at intervals of 10. Now wind direction is always measured from the true north and in clockwise direction. Then wind speed. So wind speed indicates how fast the air is moving horizontally. Then it is measured in knots, which is nautical miles per hour. Then all common units are kilometers and meters per second also. Now 1 meter per second is equal to 2 knots, or equal to 4 kilometers. Now reporting of wind speed. So wind speed are reported in steps of 5 knots. So 0 to 2 is calm, 3 to 7 is 5 reported as 5, 8 to 12 is reported as 10, 48 to 52 is reported as 50. So standardized reporting system is there for the easy interpretation for the pilot. Then comes the crosswind. So runways are normally aligned with the most frequent occurring wind direction of a particular location. Okay, now this alignment is decided for a long term by using long term wind records, so that the aircraft usually can take off and land into the wind. Now, however, the wind do not blow in the same direction. They may deviate from the normal runway direction. And when it blows 90 degrees to the runway, then it is called crosswind. And that part of the wind which is perpendicular to the runway is called the crosswind component. Now, specified maximum permissible wind component is called the crosswind component, which is given by the manufacturer. Then comes the whenever the crosswind component approaches or exceeds the critical value, great caution has to be exercised, and it can swing your aircraft, and it is more pronounced in lighter aircrafts, which can be easily deflected by wind. Then comes the instrument which measure the wind. So surface wind can be measured by two main components: the wind speed by anemometer, wind direction by wind vane. Now upper winds are also of great importance. So raven, which is radar wind equipment, it is used at high altitudes. And pilot balloon, also called Pibel. Hydrogen is filled in these balloons, and Raven method, it is tracked by radar, and pilot method basic by a basic optical theodolite. Then by observing the movement of the balloon, the speed and direction of the upper winds are determined. Then comes the exposure of the wind instruments. So to accurately record the surface wind, the anemometer and wind vane are installed at a height of 10 meters from the ground level. Now they are also placed in an open area which is free from obstructions, because wind flow will not be disturbed there. Then for general weather observation, the readings are averaged for 10 minutes. And for aviation purposes, it is averaged for 2 minutes, which makes it for more current and more relevant wind information. Then comes gust and lull. So gust is a sudden, irregular, rapid increase in wind speed, occurred due to turbulence, which is due to the ground friction and uneven heating of the Earth's surface, commonly during the hot afternoons. Now, when the wind speed increases suddenly, it is called gust, and when it decreases suddenly, it is called lull. Now, positive fluctuations are called gusts, and negative fluctuations are called lulls. Then comes what is a squall. So, squall is defined as a sudden increase in wind speed of at least 32 kilometers per hour, and it must last for 1 minute, and the wind speed should rise to 44 kilometers per hour. Then squall is associated with large CB clouds and violent convective activity, and a squall can extend for several kilometers horizontally and 1,000 feet vertically. Okay, now during a squall, both the wind speed and wind direction may change suddenly and also differ greatly from the prevailing winds. Now, violent squalls are commonly experienced in nor'westers, then during thunderstorms and dust storms. Now, these are the frequent These are frequent during the months of March to June. Remember this: March, April, May, and June. And line squalls are usually ahead of a cold front and may also occur with nor'westers. Now comes the difference between squall and gust. So the main difference between a gust and a squall is the duration. A gust is a short-lived increase in wind speed, which lasts only for a few seconds, and a squall, on the other hand, is a sudden increase in the wind speed that lasts for several minutes. Okay, and squall is also associated with CB clouds or thunderstorms, and which is accompanied by a marked fall in temperature and also rain or other precipitation. Now comes the dangers of squall. Now, a sudden or strong squall are more dangerous than a strong steady winds. A parked aircraft may be able to withstand a gale, which we'll study further, with a which is a persistent mean wind of 34 knots or more, but it cannot sustain the squall. And however, the same aircraft may not be able to withstand the sudden squall of gusting of 60 knots. So if the mean wind does not reach the gale force, okay, then the sudden impact or rapid change in the wind during a squall can damage the structure of the aircraft, and also it can make the aircraft lose its control if it is flying. Then comes gale. So gale is a persistent mean wind of 34 knots or more, and it is usually associated with depressions and cyclonic storms. So remember this, DC. Then, unlike squalls, gales are steady and sustained and not sudden. Okay. Now comes backing and veering. So backing refers to the change in direction in anti-clockwise direction. Then veering means change in direction of in the clockwise direction. Now in the northern hemisphere, in a low pressure area, the anti wind blows anti-clockwise and therefore it backs. And then in high pressure area, the wind blows in a high pressure area, it blows clockwise. Okay, therefore it veers. Then comes the pressure and wind, which is Bayes Ballard's law. So the law states that in northern hemisphere, if an observer stands with his back to the wind is blowing and here is the back. So the left low pressure lies to the left, high pressure lies to the right. Okay, and in the southern hemisphere, both are reversed. So high here and low here. Okay, so now we'll start with the effect of Earth's rotation on wind. So I want to tell you that this topic is very important for your exam, and but more than that, it is very important for you to understand the logic, because once you understand the logic, you'll never forget it. So first, we'll understand one very basic fact, which is that the Earth is not standing still. Okay, it's continuously rotating, and it rotates from west to east. Okay, remember that it is rotating from west to east. This means if you are looking at the Earth from the North Pole, if you are at the North Pole, if you are looking at it, it rotates in an anti-clockwise direction. Remember this, in an anti-clockwise direction. And this rotation is continuous and it happens all the time, day and night. Okay. Now, air is present all around the Earth. Okay. Air is free to move. And when air starts moving from one place to another, okay, the rotation of the earth affects this motion. Now, to understand this effect in a very simple way, let us imagine a small experiment in our mind. Okay, imagine there is a flat circular disc in front of you, like a round plate. Okay, and this disc is rotating from west to east. Okay, so it is rotating now exactly like the earth, it is rotating. And now imagine you're holding a pen and you try to draw a straight line from the center of the disc to the outer edge while the disc is rotating also. Okay, now you try your best to draw the straight line. Now suddenly the disc stops now rotating. The disc stops rotating, and you look at the line you have drawn. What you will notice is that the line will not be straight anymore, it will appear to be curved. So a very important point here is, from your hand's point of view, you try to draw a straight line, but because of the disc was rotating under your hand, the path looks curved when observed from outside. Okay, this is exactly what happens on the earth. Now the air also tries to move in a straight line from the center to here. Now air always wants to move in a straight line. Why? Because of inertia. Okay, but the earth is rotating under the moving air. The moving air is above and earth is rotating under it. So when we observe the motion of the air from the earth, it does not look straight, it looks curved. Okay, it will be slightly curved. Now this curving or bending of the path of moving air is because of the earth's rotation. Okay, remember this. Now Now comes a very important rule, which is directly asked in your DGC exams. In the northern hemisphere, any moving object, whether it is air, wind, a missile, or any aircraft, it is deflected to the right of its direction of motion. Deflected to the right of its direction of motion. And same in the southern hemisphere, any moving object is deflected to the left of its direction of the motion. So remember this. Okay. Now, please understand this clearly. The object itself is not deciding to turn left or right. Okay. The Earth is rotating beneath it. So, from our reference frame on Earth, it looks like the object is being deflected. Okay. And this deflecting effect is caused by the, which is due to the Earth rotation, is called by the Coriolis force, and also called geostrophic force. Got it? Now, many books are calling it geostrophic force, but for DGC exam, both names are used. But Coriolis force is the most common term. Okay. Now, I want you to mark here that the to understand the rotation of Earth affects moving objects like wind, let us imagine an experiment. If you put a disk rotating from west to east and draw a straight line, and you will not, because when you stop the disk immediately, you'll notice that the line appears to be curved to the right. Okay, this exactly happens on the Earth. This is what happens. Okay, now because the Earth rotates from west to east, the air is deflected due to the rotation, and in the northern hemisphere it deflects to the right, and in the southern hemisphere the moving object is deflected to the left. Okay, now this deflecting effect is caused by the Coriolis force, also called geostrophic force in some books. Now, what exactly is Coriolis force? This is extremely important to understand. So Coriolis force is basically not a real force. Okay, it's not a real force, not a real force like gravity. Gravity actually pulls object downwards. The Coriolis force does not push air, or it does not pull the air. Okay, it is called an apparent force. And apparent basically means it appears to exist because we are observing the motion from the rotating frame, which is the Earth. Okay, now the Coriolis force acts at 90 degrees, which is perpendicular to the direction in which the air is already moving. Okay, it does not start the wind, it only changes the direction of the wind after it has started to move. Okay, now so remember this line clearly for your exam. Pressure gradient force starts the wind. Okay, and Coriolis force only deflects the wind. Remember this. Okay, now let us look at the formula for Coriolis force. It is uh, F. The formula is F equals 2 omega V sine, and this is called phi. Remember this. Okay, now omega represents the angular velocity of the Earth. Then V, so basically angular velocity means how fast the Earth is rotating. Remember this. Earth rotation speed, how fast the Earth is rotating. Okay, and then the value is constant because the Earth is rotating at a constant rate, as we know. Now V stands for the wind speed, and it is very logical, because if the wind is moving faster, the deflection will be stronger. Okay, and if the slow moving air will be deflected less, the fast moving air will be deflected more, obviously. Then comes phi, which is the latitude. Okay, now at the equator, the latitude is 0 degrees, and it increases as we go up. Now sine 0 is 0, so at the equator the Coriolis force will be 0. Remember this, at equator Coriolis force will be 0. Okay, now that means there is no Coriolis force at the there is no Coriolis deflection at the equator. It is a very common example question which you can remember. Now remember, at the poles, and rho is the density for a fixed unit. So remember this all. Okay. Then comes the key points. So at the poles, the latitude is 90 degrees. Okay. And sine 90 is 1. So at the poles, the Coriolis force will be maximum. This means the deflection will be the strongest at the poles. Now, as you move from the equator towards the poles, the Coriolis force is increasing. Okay. Gradually increasing. So remember this. Okay. Okay, now comes the density factor. So if you see, dense air is affected more. Okay, thin air is affected less. Now that is why, because uh, the Coriolis force is more effective higher up in the atmosphere, where the winds are strong and organized, and it is very less noticeable near the surface, where the friction and the obstacles are disturbing the flow. So remember this logic. The Coriolis force is directly proportional to the speed of the air and directly proportional to the air density. Faster and the more faster and the more dense the air will be, more deflection it will feel. So remember that Coriolis force is an apparent force. It does not push or pull the air itself, but it acts perpendicular to the direction of the motion, which causes it to curve. So remember this line. Then comes the formula. Also remember the formula. F is equal to 2 omega v sine phi. Then comes the key points. So at the pole, the latitude is 90 degrees, so sine phi will be 1. So the Coriolis force will be maximum, and at the equator it will be 0 if you put the sine value. Then comes the Coriolis force is directly proportional to the speed of the air. So how faster it is, so the more faster, the more force, and the more density, then the more Coriolis force. Okay, that is, now this is why the fast and dense air masses are deflected more strongly. Got it? Now, before we combine these forces, you must understand one more force, okay, properly, and that force is the pressure gradient force. Pressure gradient force. Pressure gradient. Okay. Now, as we know that wind does not start because of the Earth's rotation. Wind starts because of pressure difference. Pressure difference. Wind naturally flows from high pressure areas to low pressure areas, which is high to low. Okay. Now, air always moves from high pressure to low pressure. Remember this. If the pressure difference is changing rapidly over a short distance, what happens? The pressure gradient will be strong. Remember this. Okay. If the pressure changes slowly over the distance, the pressure gradient will be very weak. Remember this. Okay. Now, mathematically, if you see, the pressure gradient force is the difference between the two places, difference in the pressure between two consecutive isobars or two places, which is divided by the horizontal distance between them. Okay, divided by the horizontal distance. Now, in simple words, if I say a closed spaced isobars means strong pressure gradient and strong wind. Close spaced isobars means strong pressure gradient and strong wind. So remember this. Okay. And widely spaced isobars. So widely spaced isobars are meaning that there is weak pressure gradient and weak winds. Okay. Now so this is a very common exam concept. Okay. Now the pressure gradient force always acts at right angles to the isobars and pushes the air directly from the high pressure area to low pressure area. Okay, it does not care about the hemisphere or anything. It does not care about the direction, or it simply pushes the air in straight line from high pressure to low pressure. Okay, so remember, before we see, we need to understand the pressure gradient force. Wind naturally flows from high pressure area to low pressure area. So the pressure gradient force is the difference in pressure between consecutive isobars divided by the horizontal distance, and it is mathematically represented as the rate of change of pressure with difference. So remember this line also, the rate of change of pressure with difference, and the PGF pushes the air directly from high pressure to low pressure, starting the motion of wind. That is it. Okay. Now let us see what happens when the both the forces are combined. Okay. Now imagine, I want you to imagine that suppose air is at rest initially. It is at rest, and because of the pressure difference, the pressure gradient force starts pushing the air from high pressure to low pressure. Okay, and the air begins to move. Okay, it starts to flow. Now the moment the air starts moving, the Coriolis force comes into play. Okay, and in the northern hemisphere, it starts deflecting the moving air to the right, and in the southern hemisphere, it deflects it to the left. Okay, now as the wind speed increases, the Coriolis force also increases because it depends on the wind speed. Okay, and at a point, one point, the Coriolis force becomes strong enough to exactly balance the pressure gradient force. Okay, and when this balance happens, something very interesting occurs. Got it? Now, the wind no longer moves directly from high pressure to low pressure. Instead, it flows parallel to the isobars. Remember this. It flows parallel to the isobars instead of directly flowing high to low. Now, this condition where the pressure gradient force and the Coriolis force are equal in magnitude and opposite direction, it is called the geostrophic balance. Geostrophic balance, it is called. Okay. Now, the wind that flows under this balance is called the geostrophic wind, which we'll cover it later. So, remember, when the pressure gradient force and the Coriolis force act together, what happens? The wind starts to move from high pressure area to low pressure area due to pressure gradient force. And as it moves, the Earth's rotation deflects the wind to right in the northern hemisphere, and eventually the wind attains a balance where it flows parallel to the isobars instead flowing directly from high to low. Now, remember, uh, in right in the northern hemisphere and left in the southern hemisphere. Now, the balance of the forces, this balance of forces produces geostrophic wind, which is typically high in the atmosphere away from the surface friction. Got it? Now we'll see what is geostrophic wind. So geostrophic wind is basically found in the high up in the atmosphere, okay, away from the earth surface, as it said. Now, this is because the near the surface, what happens? The friction disturbs the wind and prevents the perfect balance. Now, it is caused by the balance, but near the surface, there is no balance. Okay, but higher up, what happens? Where the friction is negligible, the balance is very well established. So you guys can remember that. Now, for example, now for your exam, always remember that geostrophic winds flow parallel to the isobars. Okay, it flows parallel to the isobars, and it occurs in the upper atmosphere. It is a result of the balance between the PGF and the Coriolis force. Okay. Now, if DGC asks why wind does not flow directly from high pressure area to low pressure area in the upper atmosphere, the answer is because of the Coriolis force. Okay. And if the DGC asks you why Coriolis force is zero at the equator, you the answer is because the sign of latitude of zero at the equator is 0 degrees. Okay. Then if DGC asks you why Coriolis force is maximum at poles, so sign is 90, which is 1. So therefore it is maximum. Okay. So always think in terms of logic, and pressure gradient force starts the wind. Coriolis force bends the wind. Okay. And so basically, once you are understanding the basic idea, what happens? The chapter becomes very easy and very scoring for your exam. So we'll start with this now. So now we'll start with geostrophic wind, and we'll see what it is in detail. Okay. Now, if you see the word, how it sounds very technical, geostrophic. But the idea behind this is actually very simple if explained properly. Now, first of all, if you ask what is geostrophic wind, so it is not something which you can feel on your face when you're standing outside. It is not the surface wind that moves the trees or the waves which you see. Okay, a geostrophic wind is a theoretical or a calculated wind, and so that means it is an ideal wind that we imagine under a perfect condition, so that we understand how the atmosphere is behaving. Okay, that is the best how you can understand. Now, this geostrophic wind occurs high up in the atmosphere, as I told you, far above the earth's surface. Okay, and what happens? It is because it is high up, because the near the earth's surface friction is present. The ground, trees, buildings, everything, the mountains, even a small obstacle like a car also, it can create friction. Now, what happens? This friction will slow the wind down and disturb its direction actually. Now, let us understand how this geostrophic wind is formed. So, it is formed due to the balance between the two forces, as I told you. So, it is formed because of the balance. Remember the word balance. You already know these forces, but we'll repeat again. because repetition builds you clarity. Okay. Now the first force is the PGF, which is the pressure gradient force, which I told you. And this force exists because the pressure is not same everywhere. Some places have high pressure, some places have low pressure, and the pressure gradient force always try to push air from high pressure to low pressure. This force is what starts the wind. The second is the Coriolis force. So Coriolis force is basically the force which exists because of the Earth is rotating. Okay, due to the Earth's rotation. Okay, now once the air starts moving, the Coriolis force is deflecting the air. In the northern hemisphere, it will deflect to the right, and in southern, it will deflect to the left. Okay, so you already know how geostrophic wind is formed when the uh, pressure gradient force and the Coriolis force act together. The pressure gradient force starts the air. The Coriolis force bends the air. When they attain a balance, it creates geostrophic winds, which is high in the atmosphere. So I hope you understand that. So if someone asks you in the exam, what is geostrophic wind, you should think like this: that it is a wind that occurs aloft, high in the air, where the friction is negligible, and it flows parallel to the straight isobars. Remember this word also, this line, that it flows parallel to the isobars, and it basically it flows parallel because the pressure gradient force and the Coriolis force are parallel, are they are basically in balance. Okay, now let's understand one very basic directional rule, which is DGCA's favorite. Now, since it is not magic, it happens because the Coriolis force right is acting to the right in the northern hemisphere, and to balance the pressure gradient force, the wind must arrange itself in such a way that the low pressure stays on the left side. Okay, always to the left. Okay, so in the southern hemisphere, everything is opposite. The Coriolis force acts to the left, so the low pressure area lies to the right of the wind direction. Okay, so remember this. Now, this is why the hemisphere is always mentioned in the exam questions. Another very important point about is about the isobar spacing. Okay, isobar spacing. So when the isobars are close together, it means a pressure gradient is strong, stronger pressure, stronger the wind. Okay, and a strong pressure gradient means a stronger pressure gradient force. Now, to balance the stronger pressure gradient force, the wind speed must be higher so that the Coriolis force becomes strong enough. Okay, this is why closer isobars mean stronger geostrophic wind. Okay, and widely spaced isobar means weak geostrophic winds. Okay, now also I want you all to understand this one mistake which all the students make. Geostrophic wind does not exist at the surface. Remember this, it is not existing at the surface. It is not a real surface wind actually, because friction exists at the surface. The balance between the forces is disturbed. So the geostrophic wind is mainly is mainly used in the weather charts, weather analysis, and the upper air motion. Okay, so, and this is why we say that the geostrophic wind is a calculated or a theoretical wind. Okay, do not panic when you see the equations. We are not memorizing anything blindly. We are understanding the relationships. Okay, so we'll mark this first. A geostrophic wind is a theoretical or a calculated wind that occurs high in the atmosphere, where the effects of the friction of the Earth's surface can be ignored. Okay, then it is formed due to the balance of the two forces. So pressure gradient force, which pushes the air, which starts the air basically from rest, and Coriolis force, which bends the air to the right in the northern hemisphere and to the left in the southern hemisphere. Remember this. Now when these two forces are exactly balanced, the wind blows straight to parallel to the straight isobars instead of directly flowing to from high pressure to low pressure. In the northern hemisphere, the low pressure area is always to the left of the wind direction, and in the southern hemisphere, it is to the right, because in the northern hemisphere, it turns right. The Coriolis force acts towards the right. Now, the closer the isobars are together, the stronger the winds. And always remember, geostrophic wind is not a real wind at the surface because friction is present. It is a calculated wind which is used in the weather analysis. Okay. Now we come to the geostrophic wind equation. So now for a unit mass of air, okay, what happens for a unit mass of air, geostrophic wind is calculated by equating the pressure gradient force and the uh, Coriolis force. Okay, And in simple words, pressure gradient force divided by density is equal to the Coriolis force. Okay, so mathematically, pressure gradient force divided by rho is equal to 2 omega Vg sine phi or theta. Okay, where P is the pressure gradient force, rho is the air density, omega is the angular velocity of the air of the earth, and Vg is the geostrophic wind speed. Got it? And this is the latitude. Got it? Now when we rearrange this equation to find the geostrophic wind, when we are solving it for this, so we get Vg equals pressure gradient force divided by the 2 into air density into omega into sine phi. Okay, so remember this. So for a unit mass of air, pressure gradient force is equal to Coriolis force because they both are balancing. And if we write it like this, to find the formula for the geostrophic wind, this is the formula. So remember this. Okay, now let us understand what this equation is basically telling us, if you ask. Okay, so since I hope you guys like to know what are the concepts behind these things. Now first, if we see, the geostrophic wind speed is directly proportional to the, okay, it is directly proportional to the pressure gradient. That means if the pressure gradient increases, if the pressure gradient here, if the pressure gradient increases, the geostrophic wind, the wind speed will increase. This again confirms that the closer isobars mean the stronger will be the wind speed. Okay. Now, second is the geostrophic wind speed is inversely proportional to the sine of latitude. It is inversely proportional to the sine of latitude. Okay, this is very important. Now at higher altitudes, the sine theta is larger. At high altitudes, it is larger near the north pole or the south pole. It is larger. So when the denominator is larger, the value of the Vg will become smaller. The value of the wind will become smaller. So at the higher altitudes, geostrophic wind speed is lower for the same pressure gradient, and at lower altitudes the sine phi is smaller, like for the equator it is 0. So the value of Vg will increase, it will be much larger. Okay, so at lower altitude, geostrophic winds is higher as compared to the other thing. Okay, now remember, now comes a very important DGCA concept. At the equator, the latitude is 0 degrees. Okay. Now sine 0 is 0. Sine 0 is 0. If you put the 0 in the denominator, mathematically the wind speed will become infinite. If you put 0 in the denominator, it will become infinite. Okay. Now obviously infinite wind speed cannot exist. Now what does this mean physically, if you ask? So it means that the geostrophic wind cannot exist at the equator. Okay, why? Because the Coriolis force becomes very strong, and the geostrophic wind equation gives a very good approximation of the actual upper winds. So remember this carefully. The geostrophic wind is best defined and most useful away from the equator. It does not exist at the equator, and in mid latitudes or in high latitudes it is possible, and where the friction is negligible at high altitudes. Okay, and if you keep this logic clear, it will be very helpful. So now we'll move ahead. So remember this also. Wind speed is directly proportional to the pressure gradient, which means the closer isobars, stronger the wind. Then wind speed is inversely proportional to the sine theta. So at high latitudes, Vg will be lower, and at latitudes, it will be higher. And at the equator, as I told you, it will be 0, which makes it infinite. So this means the geostrophic wind cannot exist at the equator. Okay, and beyond 30-degree latitude, the formula gets a good approximation of the actual upper wind. Got it? So now we'll move ahead for the limitations of the geostrophic rule. So till now we have understood what geostrophic wind is and how it is working and how is it made. But now comes a very important question, that uh, does the geostrophic wind always exist everywhere in the atmosphere? And the answer is no, because it only works under a certain conditions, and we'll see all those limitations and conditions, because there are a few limitations which the geostrophic rule has. Okay, now we'll understand it slowly. So the geostrophic wind formula works properly only when some very specific conditions are satisfied. Okay, that is it. First condition is that the isobar must be straight and parallel. Remember this, the isobar must be straight and parallel. Straight means they should not be curved or anything, they should be exactly straight. Okay, and parallel means they should not be converging or diverging. They should not be doing this. And this condition is important because geostrophic wind assumes a very simple pressure pattern that is straight. So remember this. Then comes the second condition, that is the pressure gradient force and the Coriolis force must be in balance. Okay, if one force is stronger than the other, suppose PGF is more than the Coriolis force, then there will be an imbalance and the wind will either cross the isobar or curve, and the geostrophic rule will fail. So because the wind has to flow parallel to the isobar. Okay, now comes the third condition, which is that the pressure must remain steady with time. Okay, that means the pressure should not be changing rapidly. It should not be changing rapidly, it should remain the same. And if the pressure is rising or falling with time, what will happen? Additional acceleration might come into the play, and the wind might not remain geostrophic. Now, if you think about a real atmosphere, is the real atmosphere always this perfect? So the answer will be no if you ask yourself. Very often the isobars are curved, very often the pressure changes with time, and very often the weather systems are developing, intensifying, weakening. What all happens, you guys must know. Now, so whenever these conditions are not satisfied, the geostrophic rule will no longer apply. Okay, so now, if any of the conditions are not met, for example, the isobars are curved, and the other another force appears because the wind is not moving along the curved path. Okay, if the pressure is changing with time, the wind speed and the direction will adjust continuously. Okay, this is why winds like gusts, squalls, land breeze, sea breeze, and mountain winds, valley winds, if you can say, and also local winds, they do not follow any geostrophic rule. Their direction and their speed are controlled mainly by the local pressure. Okay, local pressure difference and the temperature differences, and also since they are near the earth, due to the friction also, not by a perfect balance of forces between PGF and CF. Okay, now, so always remember this exam point clearly. Geostrophic wind does not describe the local winds or any sea breeze or land breeze, and the geostrophic wind does not describe the local or the surface winds. It is an idealized concept which is mainly based for the upper air analysis, high altitudes. Okay, so remember this, the geostrophic wind formula works well only under certain conditions, and these conditions are: the isobars must be straight and parallel, the pressure gradient and Coriolis force must be in balance, the the pressure must remain steady with time, and if any of the conditions are not met, for example, isobars are not curved, isobars are basically curved, and pressure changes over time, then other forces are coming into the play and the geostrophic formula is no longer applied. Got it? Now winds which are gust, squalls, land breeze, sea breeze, and other local winds, these do not follow the geostrophic rule, and wind and direction differ from the geostrophic wind. So what happens? However, in the mid latitudes, geostrophic wind still provides a good approximation about the actual upper air wind. Got it? So, however, within all these limitations in the mid latitudes, the geostrophic wind is actually the upper air wind. This is why the meteorologists still use it extensively. So, do not think it is useless. It is still useless. It is still useful, but only for the correct context. Okay. Now let us move to another very important type of wind, which is cyclostrophic wind. Okay. Now the word again sounds very complicated, but the idea behind it is actually very logical. Okay. So we'll start with cyclostrophic wind. So cyclostropic wind actually occurs when the wind moves along the curved isobars with a certain center of radius, with a certain radius of the curvature. Okay, now the radius of curvature simply means that how sharp the curve is. If the radius is more, this it is like this. If it is less, it is like this. Okay, so a small radius means a very tight curve, and a large radius means a very gentle curve. Okay, now whenever an object moves along a curved path, some special physics come into the play. Remember this, when it is moving in curved path. Like suppose it only not happens to the wind, but also with cars on a curved road, or stones which are tied to a string and rotated. I hope you guys have done that in your junior classes. Now, when when an object is moved in a curved path, it experiences centripetal acceleration. Okay, now centripetal force acts inside, centrifugal acts outside. Remember this. Okay, so centripetal is the uh, center seeking force. This acceleration always acts towards the center of the curve. Suppose this is the curve and the car is moving like this, or the wind is moving like this, the centripetal force will act inwards towards the center of the curve. Okay, now the formula for the centripetal acceleration is v squared divided by r, uh, v squared divided by r, where v is the speed of the object and r is the radius of the curve. Now if you apply this to the wind, if you are applying this to a wind, when an air particle moves along a curved isobar, it must experience centripetal acceleration towards the center of curvature. Okay, obviously. So for a unit volume of air, the centripetal force required to keep the object, to keep the basic air moving along the curve, is equal to the air density, which is multiplied by the v rho multiplied by v squared divided by r. Got it? Now here comes the key idea of the cyclostropic wind. So in some situations, especially very close to the center of small intense systems like a tropical a tropical cyclone, or basically you can say tornado, or a or that is basically you got. I hope you understood. So the Coriolis force becomes very small compared to the pressure gradient force. It becomes very strong, very strong. Okay, very small, sorry. So why does this happen? Because these systems are very small in size. Okay, uh, because they are very small, so the Coriolis force depends upon the scale of motion, and also all the latitude also, how higher you are in latitude. So in very small systems, the Coriolis force will be very weak. It will be weak. So remember this. Okay, so if the Coriolis force is becoming negligible compared to the pressure gradient force, then what will balance the pressure gradient force? The answer will be centripetal force. It will be provided by the centripetal force. Okay. Now in cyclostropic motion, the pressure gradient force provides exactly the centripetal force which is required to keep the air which is moving along the curved path. Okay. So in this case, the pressure gradient force equals to rho v square divided by r, or v is equal to if we rearrange this, v is equal to under root PR upon rho. Got it? Now, this type of wind motion where the pressure gradient force balances the centripetal force and Coriolis force is getting ignored is called the cyclostropic motion. Got it? So if we try to define the cyclostropic wind in very simple words, cyclostropic wind means it is a wind that blows along the curved isobars where the pressure gradient force balances the centripetal force and friction is ignored. Okay. Now this type of wind is mainly found in near the centers of the tropical revolving storms like tornadoes and you must have heard dust devils. Okay, tornadoes or dust devils, and other strongly curved winds systems, whatever. Okay, so we'll mark in this, the a cyclostropic wind occurs when the wind moves along the curved isobars with a certain center of radius. Okay, now a moving air particle along a curve experiences certain centripetal acceleration towards the center. So if the Coriolis force is negligible compared to the pressure gradient, then the pressure gradient must be balanced, must provide this centripetal force. So this type of motion is called the cyclostrophic motion, and it occurs near the center of the uh, revolving storms like tornadoes and other things. Then cyclostrophic wind is the wind which blows along the curved isobars, where the pressure gradient balances the centripetal force and the friction is ignored. Got it? Now let us move to the next and very important concept, which is gradient wind. Okay, so gradient wind is actually a correction to the geostrophic wind. Okay, which we studied, which is the balance. Okay, so it is a correction to the geostrophic wind. It actually makes the geostrophic winds more realistic, more accurate. Okay, now remember, the geostrophic wind assumes straight isobars. Okay, it assumes straight isobars, and but in reality most isobars are curved. Okay, especially around high and low pressure systems, they are like this, they are curved. Okay, now a gradient wind is calculated wind that blows parallel to the curved isobars under the combined effect of the three forces, which I'll tell you. Okay, now the three forces are the pressure gradient force, the Coriolis force, and the centripetal force. Okay, now friction is still neglected in the gradient wind, just like the geostrophic wind. So gradient wind is also a upper air concept which is played in the high altitudes. So gradient wind is more accurate than the geostrophic wind in the mid latitudes, and because in the mid latitudes the isobar are usually curved rather than being perfectly straight. Okay, they are usually curved. Now, uh, in a now let's understand how gradient wind works in a cyclone. So we'll mark this. Gradient wind is calculated wind that blows parallel to the curved isobars under the combined effect of the PGF, the CF, which is Coriolis force, and the centripetal force. And it is more accurate and more realistic than geostrophic wind in the mid latitudes, where the isobars are usually curved. Okay, then friction is neglected in this calculation because it is a high altitude wind. Okay, now we'll understand how the gradient wind works in a low pressure system, which creates a cyclone. Okay, now a low pressure system, pressure decreases towards the center. It is highest outside and it decreases as we go towards the center. So the pressure gradient is always acting inwards towards the low pressure area. Okay, now when the wind flows along the curved isobars around a low, it is following a curved path. So the centripetal force is required, and this centripetal force also acts inward towards the center of curvature. Now, what about the Coriolis force? Now, in the northern hemisphere, the Coriolis force acts to the right of the wind direction. We have studied this. So, for cyclonic flow, this means that the Coriolis force acts outward away from the center. Okay, it will act away from the center. Coriolis force acts outward, pressure gradient and centripetal acts inwards. Okay, now if you observe carefully what is happening, the pressure gradient force and the centripetal are acting outward, and Coriolis is acting. These two are acting inward, and this one is acting outward. Now, if you want to maintain the steady curved flow, which is the part of the pressure gradient force, is used to uh, provide the centripetal force. A part of this is used to provide this. Okay, and the remaining part of the pressure gradient force is balancing this, which is the Coriolis force. Okay, now because some of the pressure gradient force is being used to produce the centripetal force, less force is available to balance this, which is the Coriolis force. Now that means the wind speed must be lower than the geostrophic wind. Okay, geostrophic wind speed. Now this is why in a cyclone the gradient wind speed uh, is less than the geostrophic wind speed for the same pressure gradient actually. Okay, for the same pressure gradient the actual wind speed is less than the geostrophic wind speed. Okay, so always remember this exam logic. In a low pressure area, low pressure system, gradient wind is subgeostrophic. Okay, it is called subgeostrophic. And basically sub means less than, sub less than. Okay, now gradient wind corrects the Remember, gradient wind corrects the geostrophic wind for the curvature of the isobars and gives a closer approximation to the actual upper surface winds. So remember this also. In a low pressure system, what happens, which is a cyclone, the pressure gradient force and the centripetal force are acting inwards along the radius of curvature towards the low pressure area basically, and the Coriolis force is acting outwards. Now the part of the pressure gradient provides the which is providing for the centripetal force, and the remaining balancing the Coriolis force. So one part of the pressure gradient force is balancing the Coriolis force, and one part is producing this. So this means for the same pressure gradient, the actual wind speed will be less than the geostrophic wind speed, which means uh, since this is providing for this and this, the speed of this will be less than the Coriolis force. So here it says, so what will happen in a cyclone? The gradient wind is therefore called subgeostrophic wind. Okay, so in other words, if you say gradient wind corrects the geostrophic wind for the curvature of isobars, giving a closer approximation of the high altitude winds. So that is it for this part. uh, Now we'll continue in the third part of the series, which will be the uh, part 3 of the wind chapter. So I hope you guys understood what I was telling, and if you have any doubt, you can drop it in the comment sections. And in the next chapter and in the next video, we'll try to complete the wind chapter along with the MCQs and also a quick revision. So thank you guys and take care.